So welcome back class. Today we are going to discuss the derivation of the capacitance of the parallel plate capacitor. So we are in this particular derivation, one result of the application of the Gauss law will be used, which is the electric field due to the thin sheet. So suppose this is the thin sheet and the surface charge density, that means the charge per unit area of this plate or the thin sheet is Q by A, right now, Coulomb per meter square. So this is the surface charge density, and if our aim is to find what is the electric field, which is the at the point P due to this thin sheet, because it is a charge body. So because of charge body, if you place a test charge at the P, that will experience a force. That means at this point P, you will get a electric field intensity at this point P. So in that derivation, we have derived the electric field E is equal to sigma upon 2 epsilon naught. Okay? This is the formula for the electric field due to the thin sheet. And in that derivation, it is very important here. This electric field is independent of the position of this point P. Okay? You see here, it is sigma, which is a constant, charge per unit area, which is a constant for a given charge body, and epsilon naught already is the permittivity of free space, which is a constant. 2 is already constant. So electric field does not depend upon the point of the interest. If this P point is close, then also the same, and if it is P is a little bit ahead, then also the value of this one is good. And what is the reason for that? It is a concept of the point of view, and that we'll discuss in the ahead. What is the concept of the point of view? When you close, the effect area of this charge body is lesser, and when you are moving ahead, then the field of view increase, and because of the effect of the charge is also increase. So that is the concept of the field of view. So already we have derived this expression. The electric field due to the thin charge sheet is sigma upon 2 epsilon naught. So this derivation, the result of this derivation is going to be used in the derivation of the capacitance of the parallel plate capacitor. So suppose we have a parallel plate capacitor, right now, and this is given a power supply, any kind of power supply is there, and because of that power supply, the charge present on this one is plus, and the second identical plate is there. Because of that, it is the minus charge built up here, and here it is the grounded. So going to happen, what is the potential? Only you have to maintain the potential difference there. Now see, suppose of this charge present on this first plate, the surface charge density is sigma, right? And because it is the vacuum in between the plates, so and it is identical plate is there. So identical plate, this corresponds the identical induction. That means if this plate has the plus sigma charge, so this plate has the minus sigma. Electrification due to the induction. So the same effect of the induction will be there. So whatever the effect of this positive charge, the same amount of the induction build up. So this first plate has the surface charge density of the plus sigma, and the second plate has the surface charge density is minus sigma. So what is the electric field present in between these two plates? Right? In between these two separations, what is the electric field? So what is the procedure to find the electric field? We have to take the test charge and just place anywhere, because in the thin sheet it is independent of the position, so you can take the P point anywhere. So if you place a test charge here, so because of this positive plate, the direction of the electric field is in this direction. Say it is E1. Right? Because of this positive plate, if you place a test charge here, so that will give the direction of the force this side. So the electric field direction is in this side. And what is the value of this E1? E1 is equal to, again, it is the electric field due to the thin sheet, which is independent of the position of the point. So it is equal to sigma upon 2 epsilon naught. Clear? And because of this second plate, which is the negative plate this side, what is the direction of the electric field at this point? So again, if you place a test charge here, that will attracted by this negative plate. So you will get the direction of the electric field is in this direction. So both in the same direction. And again, what is the magnitude of this E2? So E2 is equal to, again it is sigma upon 2 epsilon. Don't be confused, I am not taking the sigma, minus sigma upon 2 epsilon because already I am indicating the direction here. So move the electric field in the same direction. So because of these two, both the plate, what is the E net present in between these two plate? So you will get the E net is equal to E1 plus E2, because both the vector quantity is in the same direction, you will get the E1 plus E2. So you will get sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught. So you will get the sigma upon epsilon naught. So this is the electric field present in between these two plates. Right? So in between these two, anywhere in these two plates, you will get the electric field is sigma upon epsilon naught. Right? But our aim is to find the what is the potential difference across these two plates due to this electric field. So I am going to raise this one. So we have the relation of the potential gradient that will give E is equal to minus dV upon dx is the potential gradient relation. Because of in electric field, if you move by a ds distance, then the potential difference build up is dV. So let us assume the potential difference across these two plates is V. That means this dV value is V. And because of we have to move the d separation in the electric field by the electric field present here. Electric field is here, and electric field from one point to another point, if you are moving by the dx separation, then the potential difference is dV. Right? Minus sign only indicates in the direction of the electric field the potential decreases. Right? And potential is a scalar quantity, that is why there is no need to worry. Right? So this is the relation between the electric field and the potential difference. E is equal to minus dV by ds. It is also known as the potential gradient relation. So here, so from this formula we can write the potential difference V is equal to E into whatever the dx. So here we have to move the d separation in the electric field. The electric field is uniform in between these two plates, and we have to move the d. So V is equal to E into D. Here, and don't need to worry about the minus sign because I am already assuming the potential difference because these two plates is V. Potential difference is V, and already the V is there, and it is a scalar quantity. So no need to worry whether it's a plus or minus. Already we have taken the net potential difference across these two plates is V. So V is equal to E into D from this potential gradient relation. So put the value of E net here. So you will get V is equal to sigma upon epsilon naught into D by putting the value of this E net. Okay. Now, so we have the value of the V is equal to sigma upon epsilon naught into T. But according to the definition of the capacitance, C is given by Q by V. So just put the value of V here. So C is equal to Q divided by V, and V is equal to sigma upon epsilon naught into T. Clear? So after simplification, that becomes epsilon naught Q upon sigma into D. And what is sigma? Sigma is the surface charge density. That means sigma is equal to charge per unit area. So from this sigma is equal to Q by A, you can write Q is equal to sigma into D. Right now? So in place of sigma, you can write Q by A. So C is equal to epsilon naught Q, and that becomes Q divided by A into D. And this Q and Q get cancelled out. So what we will get? C is equal to epsilon naught A by T. So this is the derivation of the capacitance of the parallel plate capacitance. Right now. So here we are using the result of the application of Gauss law, where with the help of Gauss law you just determine the electric field due to the thin sheet. And here we have the two thin sheet, that is why we will find the net electric field present in between these two plates. And because of that electric field, what is the potential difference across these two plates? So with the help of potential gradient relation E is equal to minus dV by dx, we can find what is the potential across these two plates. So after that we have the basic definition, C is equal to Q by D is the basic definition of the capacitance. Just put the values, and after simplification you will get C is equal to epsilon naught A by D. So the capacitance of the parallel plate capacitor depends upon the epsilon naught, which is the permittivity of the free space, which is relate the dependency of the medium, and A, it is the surface area of the plates, and D is the separation between these two plates. So this is your formula, C is equal to epsilon naught A by D. I hope you understand this derivation. If you have any doubt, you should mention in the comment section.